Good afternoon, everyone. Welcome to another of our TDS webinars. Today we have Peter Robinson from PNGFP talking about the evolution of plywood decking in timber bridges, which I'm really looking forward considering the Timber Bridge Conference is coming up soon. Before I introduce the speaker, thank you to all of you for joining, obviously, and also to our sponsors for making this webinars possible. You see our sponsors in the bottom, and I would like to specifically mention iBuild, being the distributors of PNGFP products here in New Zealand. As mentioned, the Timber Bridge Conference is coming up on the 29th of June in Rotorua, and it would be great to see you all there listening to national and international timber and timber bridge experts talking about the future of timber bridges in infrastructure. If you are a TDS member, you get $100 off of the registration fees up there. Just email the conference organizer and you get a discount for the conference registrations. In terms of research scholarships, you have about another month to apply. If you are a researcher and working in the timber field, you're eligible to a scholarship from TDS, with the only condition that you then supply a paper to the TDS journal. The next TDS webinar is going to be on the 19th of June, and it's Andrew Carlson from the School of Architecture at the Victoria University in Wellington talking about inspirational timber design with about 20 case studies he has visited and studied around the world, and he will share his insight on those timber buildings. Back to today's webinar. So Peter Robinson, he is a strategy and development manager at PNG Forest Products, and he's responsible for the development and commercialization of engineered wood products. He worked in the industry for several years. He worked especially in the field of R&D and manufacturing. And he has not only looked after the commercial sides, but he also very knowledgeable when it comes to technical aspects and has worked on several standards committees for national Australian and or New Zealand standards. Now, his presentation is about bridge decking panels and the evolution, how they started from large-scale plywood panels used as a replacement for traditional rattle boards on Australian bridges over to the Bridgewood, which was marketed in the 1980s as a CCA Envelope treated product, over to the current product from PNGFP, which is a very flexible, lightweight, robust deck paneling system. And it really helps us designing timber bridges. If they're pure timber or hybrid, doesn't really matter, but it's an addition to the suite of materials we can use for sustainable bridge design. With that, I pass over to you, Peter. I'm really looking forward to your presentation. And obviously, all of you, if you want to learn more about this product and bridges in general, come to the Bridge Conference. Peter Robinson will be there. His company is one of the sponsors, actually the platinum sponsor. There will be samples, there will be a bridge model to look at, and there will be a lot more knowledge to be gained if you join the conference. Thank you very much, and over to you, Peter.
Thank you, Daniel. Just let me share my screen. Right. Thank you for the introduction. And before we get into the topic of the evolution of plywood decking in timber bridges, I'd firstly like to introduce PNGFP, which is one of the first members of the Engineered Wood Products Association of Australasia, which, for those old of us to remember, that was formerly the Old Plywood Association. The story of PNG Forest Products really starts back in the early 1930s, when Boral Gold Dredging Limited was developing an extensive alluvial mining operation in the Boral Valley. Weighty mining plant and hydroelectrical, to facilitate this large-scale operation, PNG reinvented large-scale air transportation to shift large quantities of machinery and supplies quickly and efficiently, a feat that had never been accomplished anywhere in the world at that point in time. Weighty mining plant and hydroelectrical equipment were flown in piece by piece across some of the wildest country in the world, noting that at that point in time there was no roads between Boral and the coast. By the mid-1930s, Boral was hosting one of the world's largest goldfields with 8 dredges powered by BGD's own hydro power stations, one of which is still operating today. Plantation establishment. As the operation grew in scale, so did the town and the need for timber. In the 1940s, the Forestry Department established a pine nursery and reforestation program, planting 60,000 young pine trees each year. This created employment by establishing the nursery and planting efforts, with this employment legacy continuing today with continual replanting. This is a photo of the rehabilitated land and re-established forest after dredging. The pine nursery and plantation, which are unique in PNG, was first established by Queensland Department of Primary Industries using gene stock from southeast Queensland. Today, the plantations are managed by the PNG Forest Authority and contain hoop pine, clinky pine, and exotic pine. Sustainable yield of 100,000 metres cubed per annum. PNGFP operates a full harvesting operation to ensure chain of custody. While the radiata pine in New Zealand has a stress grade of F8, F5 or F8 with a maximum of F11, by comparison, the hoop and clinky have stress grades of F14 to F17 with a small segment of the crop having stress grades approaching the Australian eucalypts at F27 or. This higher strength property is a key point of difference when designing timber bridges. Hence, when we go back in time, the default stress grade for plywood bridge decking is F14, which was started by Hancock Brothers with the first product in 1985. No surprises, timber-based products are the ultimate renewable. Every 30 to 40 years, we are harvesting from the same compartment. When mining operations scaled down, BGD constructed the largest plywood factory in the Southern Hemisphere at that time under the name of Commonwealth New Guinea Timbers Limited, which was 50% owned by the Australian government. The ply mill consisted of a 5-acre under-roof building, and in 1954, plywood production and the export of product overseas commenced, signaling the birth of a new industry in PNG. Continual upgrading and expansion over the years has evolved the site into a fully integrated facility containing ply mill, sawmill, treatment plant, joinery, secondary processing, with a focus on sustainability and maximising the value from the fibre. While most ply mills, our competitors, will peel a log down to 75 to 110 millimetres and chuck a peeler core out, and then that gets chipped. What we do differently is we take that same peeler core and put it on a newer spindless lathe and peel the 110 mil core down to essentially a broomstick with a final diameter at about 38 millimetres. This then salvages a valuable extra couple of sheets of veneer from every billet we peel. Part sheets are then defect docked. Is that glitching? That defect docked and then edge glued back together in a core composing operation, thus salvaging further product from the wood fibre. Sawdust, wood chip waste, and from the mill are used as fuel for the boilers, providing steam for the veneer dryers hot presses and kilns. Our facilities in Boral are powered by PNGFP's own hydropower station, one of which was established by BGD back in the 1930s. Inside the old station, which continues to run today, albeit with a bit of updating of control equipment, which runs alongside the original meters, which you can see in the top left-hand photo, still going. We continue to invest in hydro, commissioning our fourth power station last year to feed a further 11.6 megawatt into the grid, raising our total capacity to 26 megawatts, 3.7 of which is used for the manufacturing facilities in Boral. Thus, the only fossil fuel used in the manufacture of our products is loaders and forklifts for the harvesting processing operation and transport to site. Quick look at our products and services. Apart from the bridge products, we do a range of commodity products and some highly specialised products. We make bus floors for trains, trams, export them to various places in the world. Do freeway noise attenuation panels. You've got on the right-hand side the Monash Freeway in Melbourne, and top left is the Gateway Arterial in Brisbane and the Eastern Busway in Brisbane as well. We produce some high stiffness flooring specific for the New Zealand market, form ply, and some modular bridging and decking system, which in particular will now look at the evolution of the decking product over several decades from 1985 to now. Plywood bridge decking started with Hancock Bros Pty Ltd, with an envelope treated CCA panel marketed as the alternative to the hardwood rattle boards. Attributes that were included in the marketing were predictable engineering properties, larger panels compared to the sawn timber boards, which reduced the number of gaps in the deck and protected the substructure from moisture ingress. Option to cantilever to widen bridges, all from a sustainable plantation resource compared to the old growth hardwood wood which was being used at that time. There are essentially two thicknesses available: 155 millimetres for the old 70 kilonewton Austrades loading and 166 millimetres thick decks for the 80 kilonewton wheel loads in AS 5100, all based on the typical configuration of a Queensland Transport Main Road A-class timber bridge. The only treatment option at that time was envelope treatment after final fabrication, which increased the thickness by approximately 10%, panels then drying in situ after installation for many months, with panels shrinking from their delivered thickness to between nominal and delivered thickness. This has implication for having to retighten bolts, with loose panels tending to crack the deck wearing surface. Installation features in this early project in Cunnamulla in Queensland were large 100 by 100 washers as tie-down bolts, channel bolted to the surface of the deck in an effort to reduce movement in the seal. TMR experienced in the early bridges a bit of difficulty holding on the deck wearing surface, and found through trial and error that putting a channel on the outside increased the adhesion of the seal. See the bitumen seal taken to the outer edges to prevent UV and moisture degradation, and through bolted guard posts. Another example of an early CCA deck which had some hardwood distributor beams underneath in an effort to minimise the reflex cracking between adjacent panels, as you can see in the bottom left-hand photo. In our timeline, we're up to the early 1980s, late 1980s, early 1990s, with research and development in progress for alternative treatment types and chemicals. But before we talk about treatment options, it's worthwhile mentioning that we should view that the first line of defence against fungal attack is detailing to keep the moisture out in the first place. Dry timber will last a long time. The second line of defence is treatment, and the greater the proportion of correctly treated wood in a structure, the lower the risk of fungal and insect failure, and hence the longer design life possible. Treatment cylinders tend to be 1800 or 6 foot in diameter, which limits envelope treated plywood panels to about 1200 millimeters or 4 foot. One way around this limitation is to treat the veneers first and then bond together. However, development of suitable chemical and bond performance took time. Benzyl iconium chloride, which was the first chemical used, but required very high loading even for H3 treatment levels. ACQ was APVMA registered as a one pot in 1995 and provided an excellent preservation solution for both bridge decks and freeway noise barrier panels. Elman Creek is an early treated deck installed circa 1995 on a traditional hardwood timber substructure. It was included in the 2016 EWPA Analytical Treatment Survey of the long-term performance of bridge and deck noise wall, which was part of the industry submission for the AS-NZS 1604 treatment standard review process. We took four core samples from this structure, and after 30 years, all the analytical results were excellent, with no issues found. The AS-NZS 1604 is the joint Australian and New Zealand treatment standard, which is a performance-based standard and details options for both chemical retention and penetration patterns to achieve each hazard class, with the same detail essentially contained in the New Zealand rounded and sawn timber standard. For H4 and H5, there are two plywood penetration patterns, being envelope and veneer, and 5 possible chemicals. Typical envelope treatment. The minimum penetration as per the standard is for both face and back veneer to be fully penetrated, together with a 150 millimeter annulus around the outside. Typically, however, with envelope treatment, penetration is greater than just the face and back veneer. However, even with longer treatment cycles, the relatively thick secondary bonds in the plywood bridge decks provide a barrier, resulting in untreated wood in the core. Untreated wood will require site remedial treatment if exposed via cutting or drilling during installation. Kinky number 1 bridge is a CCA Envelope deck on steel girders, headstock, and distributed beams with hardwood piles. The deck is approximately 30 plus years old, with an asphaltic concrete deck wearing surface, Queensland Transport Main Road asset with a local nearby quarry and secondary access to the Tuantalara pine plantation. Maintenance conducted in October 2024 after soft section of deck were identified. After stripping the bitumen, the majority of the panels were still serviceable, except the narrower cut panels over headstocks. These panels had the outside veneers intact, but exhibited decay in some places on the inside. Only the defective panels were replaced and the structure returned to service. These deck panels have had a service life so far of approximately 30 years and majority still in service. It is a robust product but could be better. We take a risk-based approach, mitigating the risk of on-site remedial treatment by utilising product advances of veneer treatment. We can aim for timber structures for a longer design life. In other words, trying to achieve a 100-year design life. The second penetration pattern in the standard is veneer treatment, which is where each sheet of veneer is individually treated in loose form, allowing preservative solution to readily penetrate the veneer. Peeler checks even allow penetration into heartwood, which is generally considered untreatable. Peeler checks are microscopic cracks that are introduced into the wood during the peeling process as the veneer is bent around the lathe nose bar. The example photo is from the standard, which was taken from a section of new deck, with the cut section then sprayed with commercialisation, which turns blue in the presence of copper. As you can see, the penetration in these peeler tracks in the middle layer of heartwood. The outside two layers are sapwood, which shows the 100% penetration. Of the waterborne chemicals for H4 and H5, only ACQ and copper azole can be used for veneer treatment. Phenol formaldehyde glues, which are necessary for the A bond required by the ASNZS 2269 structural plywood standard, are not compatible with CCA treated veneers or oil-based preservative options. Treating the veneer first prior to plywood manufacture firstly ensures 100% penetration and thereby minimising the risk of failure, but also delivers a dry, less than 15% moisture content panel, which will not shrink in situ after installation. The 100% penetration ensures that even after drilling and cutting, there is no exposed untreated wood, thus minimising the risk of failure. In addition, dry panels tend to have better seal adhesion, even for the traditional bitumen-based coating, as well as the newer epoxy coatings. As I mentioned earlier, seal adhesion on the early CCA treated envelope products was an issue, hence the channel on some of the earlier examples of CCA treated bridge decks in service to reduce the movement of the seal. New Deck is a robust veneer treated decking system that's undergone a risk assessment process with the Australian Rail Track Corporation and deemed suitable for rail deck applications. Examples shown in the photo is the railway flyover for the freight line on the freight line to the Port of Botany. Sustainable option for replacing scarce large section hardwood transoms with the added benefits of reliable engineering properties, 50-year treatment warranty, debris protection for the 6 commuter rail lines that run underneath this bridge, and reduction of trip hazards for maintenance personnel. Installed during a 3-day period over Christmas, all 6 suburban lines in Sydney needed to be shut down and power turned off to the overhead wires to facilitate the work. Specific panel widths were needed to fit between the cross members, with rail plates directly fixed to the panels. Surface coated with bitumen seal for slip protection as well as moisture and UV protection. Key design attributes that ARTC looked for were the robust preservation, availability, high strength, debris protection, noise reduction for surrounding residents, and a contiguous surface. Moving back to road applications, Queensland Transport and Main Road 7-span bridge at Eel Creek, just west of Gympie, which is a 2-lane secondary road with a relatively high traffic volumes. Detailing in the photos, end grain sealing of both the whalers, girders, guardrail distributor beam, which is trying to spread the load between adjacent panels for the guardrails, flashings on the edges of the entire deck, distributor beams mid-span or mid-spacing between the girders to reduce the reflect cracking on the seal above, and sealing to the edges. Suitable for restoration and conversion of historic rail bridges. This is an example on the Tweed section of the Northern Rivers Rail Trail in New South Wales, where specific panels were made for differing sections of the bridge. The approach trestles had panels laid perpendicular, while the panels on the main bridge were orientated parallel to fit in with the historic structure. Here's a couple of shots of the old structure, of the trestles and the main structure. A photo of the before and after of the trestles approaches. This bridge is now part of a 66-kilometre walking, running cycle track rehabilitated from the region's former rail line. And speaking of historic bridges, New Deck was the product of choice for redecking the oldest wrought iron bridge in New Zealand, Rakaya Gorge Bridge. The product was chosen due to its lightweight, durability, low capacity, ease of installation, and a proven track record. Even nominated for an Innovate NZ award. With this project in Napier in New Zealand, New Deck panels were pre-assembled in a workshop, then delivered to site in a kit form, a bit like a set of Meccano, then lowered into position and assembled, and overall resulting in a very quick installation times. Veneer-treated plywood decking also offers flexible design options to extend and upgrade existing public infrastructure assets. This example, Waimakariri, is an old rail bridge. Recent project where the flexibility was used, we made 2-metre wide panels rather than the standard 1200mm wide panels. This was to suit the guardrail post spacing, so each post was right in the middle of the panel, that's distributing the load. Also 2-metre panel spacings also reduced the number of joints in the deck, which helps with any reflex cracking and adhesion of the deck seal. Dimensions typically are constrained by economic transport. Panels can be up to 12 metres in length, up to 3.6 metres wide, and maximum thickness are approximately around 300 millimetres. The rail deck applications that I showed earlier also have an LVL core for the higher loadings. Here's another example, same example, sorry, just putting the seal on. And in the end, plywood decking looks like a very good example. One of the challenges facing traditional timber bridges rehabilitation is that large end section girders are getting harder and harder to source, resulting in a greater proportion of the timber bridges, being replaced with concrete structures. This led to a development of a modular bridge system, where LVL girders were integrally bonded to a contiguous deck, resulting in increased structural performance due to the composite action between the deck and the girders. Boral Hancock Plywood, which was the old Hancock Bros Pty Ltd after the assets were purchased by Boral, developed and installed the first modular bridge in 2009. Unfortunately, the business closed in 2011 as a result of the 2011 Brisbane and Ipswich floods. The product was further developed by PNGFP into Newbridge, which is a lightweight prefabricated modular bridge system that combines both girders and decking, offering a fast, cost-effective, reliable solution for short-term and long-term bridging solutions. Easy to transport, modules up to 15 metres in length. This is a project near Gympie for the Gympie Regional Council. It's a bridge replacement designed to pair us fibre reinforced spread footing abutments. Elastomeric bearing pads were put down to minimise wear on the base of the girders. Bridge lifted in came pre-assembled on one semi-trailer, as you can see there. The first section was lifted in place, mate lifted down beside it, bolted together and tied down to the abutments, and complete finished structure. Newbridge, we got single lane, multi-lane, two essential design loadings for T44 and also SM1600 in the AS5100 code, and can do custom loadings if required. Undertaken full system testing at UTS in Sydney, breaking full destructive testing, taking our product to beyond what it should normally be loaded to. So to recap, we started the plywood bridge decking journey in 1985 with a CCA Envelope treated product. Veneer treating process with ACQ was commercialised in 1995, allowing greater size, flexibility and a dimensionally stable product. Early volumes of these products were sold into noise barrier and bridge decking markets. Processes were further refined to allowing for a 50-year treatment warranty. Integrated deck girder modules were introduced in 2009 with a combination of product testing and risk assessment. The decking product is now used in both road and rail applications for a variety of load conditions. Thank you.
Thank you, Peter. Thank you very much for your presentation, and thank you for talking us through the history of plywood bridge panels. It was certainly interesting to see both the manufacturing side of things, but also the actual application in real projects. So we have a few questions coming in. The first one I saw was about the interface of the decking panels with the guardrail. The question is, you have this rather small areas where the guardrail is sitting against or on the decking panels. Mm-hmm. Do you have any experience of how they behave if there's an actual crash? Can the panel cope with those loads?
Yeah, the panels obviously can cope with the loads. There is an extra detail that on the underside, so you got the post on the top, and then underneath you have a backing plate. one of the additional details that you can do is put an inverted PFC on the inboard set of bolts, which runs transverses across multi-panels. So when you get an impact, obviously, that shares the load to many bridge panels. And not that I have a photo of it, but the posts tend to shear off the base plates.
Looking at the other questions
Question.
coming. There's one question about the steel channels, which you have shown, and I noticed they're also in your technical literature. Would you recommend them as a typical solution also for ordinary bridge deck replacements?
The which channels? The
channels which are limiting the movement.
Underneath, yes. Yeah, look, given there's no jointing system between adjacent panels, when you've got a wheel on one panel and it goes, obviously that deflects, and then it goes to and the adjacent panel is not loaded, you get a differential deflection as the vehicle traverses the bridges, which does tend to induce cracking in the deck wearing surface, which from the product's perspective isn't an issue. It's not overloaded, and the moisture ingress doesn't cause concern to the product because of the veneer treatment and the extra moisture coming down. But yeah, the distributive beams underneath certainly obviously share the load between adjacent panels and do reduce the differential cracking. So in the photo I showed, the girder spacings were quite close, and so if you think about it, I think it's probably only about 400 or 500 millimeters unjointed in those photos, with the about a meter spacing between the big girders. So would I recommend it? Yes. Certainly for higher load, higher traffic load structures. For the very secondary roads where you get just a handful of cars, probably not worth the expense, but I guess it's a trade-off between functionality of what you're trying to do and performance.
Out of my own curiosity, have you considered or have you ever seen other type butt joints where instead of just butting them, you could have a half lap or a tongue and groove type connection?
Yeah, we have tried a half lap, but I guess if you do a half lap, it's great one way, but not the other way. Tongue and groove, yes, but I guess the downside of doing something like that is you have the potential to introduce a moisture trap. If you do a traditional tongue and groove, moisture will get in. So have we thought about it? Absolutely. Is it something we're trying to work towards? Yes, we are. You need a jointing system that limits the movement between adjacent panels, but it also is free draining, so you can't trap the moisture in there, because you may end up solving one problem, but then introduce another problem by trapping that moisture in there.
Yeah, thanks. I think that last sentence is probably very, very important to keep in mind. Thank you. A quick one here would be, what product are you using to seal the edges of your decks or girders?
Look, as standard, we put 3 coats of a good quality acrylic paint. Now, acrylic paint is a nice flexible membrane. Given that the majority of, once it's installed, the paint's never seen, you don't want a brittle membrane, because once let's face it, a lot of these structures are overtopped with water. So they will, once they're installed, they will the panel thickness will cycle based on changes of EMC. So in an overtopping situation, the panel will suck up a bit of moisture and expand, but then that will gradually reduce once floodwaters subside and et cetera, But you don't want a brittle membrane on the edges, because that will crack during the expansion, and then you've got no sealing and you'll just get moisture continually through that crack in them. So you want something that can expand with the and contract with the cycling of the bridge deck thickness over its life.
Thank you, Peter. Another question, probably partly a statement, is the product you're selling has much higher properties than we typically see in New Zealand.
Yes.
Are you also exporting other products like Lulam or LVL?
No, look, our mill is set up for plywood. We do make short length LVL, basically LVL and plywood presses. We don't have a long LVL press like other companies in New Zealand. The LVL that we do make is jointed in a scarf jointing process and ends up in our rail deck that I showed in the presentation, which has higher loadings requirements. We blend plywood and LVL to match the properties of the panel to the design loads. The other LVL, scarf jointed LVL, we do is bottom of those modular bridges. So those are underneath LVL girders, cold laminated together, scarf jointed. They're veneer treated just like the plywood decking solution, and they have a resorcinol bond between the girder and the deck, so that provides your composite action. So it's a bit like a super T beam. If you go to concrete, you've got the bit on the top and the bit underneath. So essentially, in timber speak, it's a few of those same geometry in a timber. So the decking is plywood, which is what you want, the two-dimensional strength. Then the beams are LVL to give you that structural performance in that plane, and they all bonded together.
What's the maximum length you can achieve with those modular?
15 meters.
Mm-hmm.
And so we've got the I guess lower T44 or equivalent loading code. We have the SM1600, which is on the Australian standard 5100. Now the difference between the two products is purely the depth of section of the LVL beams to minimise deflection. Both structures are deflection limited, not strength limited. But that photo I showed on the transportation, you saw sort of 15-metre module hanging over the end of a flat rack. Now, a flat rack in shipping speak is 12 metres long. So we can ship transport 15 metres. It's classed as outer gauge in the shipping world. Tends to be the limit, even when you get to your destination of economic transport without going to permits and what have you.
Now, obviously, your presentation had a heavy focus on bridges, but have you used your products for vertical structures as well? Or do you see application in moving forward?
Have we used them for vertical structures? No. Could they be useful? Absolutely. If you think about it, it is purely a large section jumbo plywood, which was a nickname it was given in the 1980s. We can deliver 12 metres by 3.6 by thickness to suit. And look, a 12 metre by even 2 metre by 300 mil thick panel, it's a large piece of plywood. There's a lot of veneers in that.
Yeah. I think there's an American company who produces a very similar product, and they mainly focus on shear walls and other structural.
Yeah. Look, aware of those guys. Yes.
Perfect. Now, talking about products, is there any other product or you're working on in terms of R&D?
We're obviously focusing on I guess a couple of areas. One is evolution of the treatment. Where do we go post CCA chemicals, given the end of life consideration for those types of preservatives. We're working on perfecting alternatives to both CCA and ACQ, which at end of life will have better outcomes. Combined with that, we're working on fire performance attributes to improve, like if you're talking about back to a bridge structure, you're talking about certainly in Australia, one of the key things that we ask, well, timber burns, doesn't it? So why would I put a timber bridge here? I can buy a concrete one type thing. All materials have their own problem. Concrete has its problem. Steel has its problems in bushfires, and timber is a pretty good actual performance in terms of timber fire resistance. Once it starts charring, the charring obviously protects the inside structure, and certainly with our timber bridges, that they're a meaty, large end section. So if you lose a little bit through char, well, it still can carry loads. So we're working on various coating type and impregnation options to be able to, in an Australian context, to have BAL 40 bushfire attack level of 40 type performance for these large structures.
Interesting. Peter, so we're down to the last, I think, 2 questions, unless some other comes up. What's your recommendation in terms of surfacing options, especially under the, like in the case of heavy vehicle loading and damp conditions? Is there any specific product or any system you would recommend at this stage?
Heavy loadings, I guess the product, old school product that tends to work and lasts the best is a thick asphaltic concrete. So put tack seal down. Tricks to it: keep the panels dry. Make sure they're dry. Talk to all the bitumen people. They don't like putting. You've got to have the panels dry for it to stick, which is probably part of the challenges with the early products, which were envelope treated, delivered, wet after treatment, dripped off, and so they took 6 months to dry in situ. A really thick, like 75mm plus asphaltic coating tends to work the best, and there's examples where you can go across an old school timber bridge and you wouldn't know what's underneath it. On the lighter side of things, obviously that comes with a penalty in terms of weight to put a thick coating like that down. Chip seals, but I guess they come with a penalty of probably having to maintain them more and maintain the integrity of the actual seal itself. There is some newer coatings on the market, some epoxy-based coatings that we're experimenting with, but if you ask me what is the tried and tested and reliable at this point in time, it'd be the asphaltic concrete AC seal after a good tack seal. underneath it. Joints would be coated with a fabric tape like Bitec, and then go from there.
Thank you. Just a little addition from the New Zealand end. There's some work underway in terms of testing some of the epoxy coatings on plywood decking, done by University of Canterbury and by Captive, which is one of the R&D outlets of NZTA Boka Kotahi. And the first results look very, very promising. But obviously some more work on that one. And I think it will be one of the topics at the Bridge conference in Rotorua. Peter, last question, and up to you if you want to answer this one, or people can contact you. Are you willing to share a rough dollar figure in terms of cubic meter of the plywood decking panel?
That's a people can contact us. Yeah, absolutely. That's a hard one because I know our essentially delivered price, but then it depends on the next level where each structure is, in terms of transport to site and all that. That's where your sponsor iBuilt comes into the picture. But if anyone has a project, wants a indicative figure, by all means give iBuilt and or myself a call, and we'll answer the question for each specific location where we're going to, because it does vary.
Perfect. Peter, this concludes all the questions we have received. So thank you very much again for your presentation. It was really, really interesting, and looking forward to use more and see more of those plywood deck panels in New Zealand and in Australia as well. And again, everyone interested in the product, come to Rotorua. There will be samples there as well, and Peter will be there as well. So thanks again, and good afternoon to everyone.
Thank you, Daniel, for the opportunity.
Thank you.